So in this video, we are going to talk about one of the basic concepts of calculus, which is rate of change, and how we can estimate that rate of change using like two different types of lines. So calculus was first developed by Sir Isaac Newton and Gottfried Leibniz to help them describe and understand the rules governing the motion of planets and moons. Since then, a lot of mathematicians have refined and developed idea in calculus and learned how to apply it to a lot of different fields. And one of the major concepts of calculus is the rate of change. So you have learned about rate of change in past math courses when you're talking about a linear function. And we also often find the slope of the linear function, and the slope is the rate of change of the y-coordinate with respect to the x-coordinate. And when we have a line, we use the classic slope formula, which is the quantity y2 minus y1 over the quantity x2 minus x1, or maybe you thought of it as rise over run. But in calculus, we're not going to really look at linear functions. We're going to look at a lot of different functions, such as exponential and quadratic and cubic and other polynomial curves, because in real life, most things are not modeled with a line. A lot of them are modeled with much more complex equations and graphs. And so as a result, we need to be able to find the rate of change of any type of graph. So how do we tell how fast a curve rises or falls when it's not linear? And the basic idea is we use something called a tangent line, and we find the slope of that tangent line. So this red line is called a tangent line, and the blue is my curve f of x. And the point of the tangent line is that it shares the same point as where we're trying to find the rate of change, but it also shares the same slope. And so this line models the slope of this curve at that point. And so a tangent line to a curve at a point is the line that best models or approximates the behavior of the curve at that point. And the function f with the slope at this point, x equals a, has two things in common with it, with its tangent at x equals a. So this curve and this green line have two things in common. The first is that point that they share, which is called the point of tangency, where they intersect. And the x value and the y value is the same at that point. The other thing is the slope of the tangent line is the same as the slope of the curve only at this point. Okay, obviously the slope of this line is nowhere close to the slope of the points over here or even up here. It's only at this point. We denote the slope of the tangent line by, it's called f prime of a. So it's f and then apostrophe and then parentheses a. And I will always say f prime of a. And the key thing is the slope of the curve equals the slope of the tangent line, again, only at that point. So at the point of tangency, which is this point here. So we are going to look at how do we find the slope of the tangent line, and we're going to first start approximating it using something called a secant line. So we use a secant line to approximate the tangent line. A secant line is a line between 2 points on a curve. And so instead of intersecting one, it intersects two. The slope is not as accurate. You can kind of tell that the slope of this line is not exactly the same as that curve, but we're going to look at how can we get it as accurate as possible. Okay, so we're going to use this example to help us see how we do that. So the graph below is the graph of y equals f of x, and we want to find the slope of the tangent line at the point 1, 2. So here's my point 1, 2, and here's my tangent line. And the problem is with this tangent line is it's not really easy to tell another point exactly that it goes through. Like I'd have to estimate anywhere. Like I'd have to estimate what this point is or this point. Like there's no clear cut point. So we can use the secant line to kind of help with that and get an estimate of the slope of the tangent line. So we're going to start by finding the slope between the points 1, 2, and 2, -1. So here's 1, 2, here's 2, -1. You can definitely tell it's not as good an approximation as that, as the blue line, but it's just going to help us to kind of get an idea of the slope. And so when we find the slope, we use the slope equation. So I'm going to do y2, which is -1, minus y1, which is 2, and then divide by x2, which is x2, which is 2 minus 1. Okay, and so that gives me -3/1, which is -3. So the slope of this red line is -3. Okay, so then what we're going to do is we're going to pick a point that's closer to this 1, 2 and estimate and find that slope. And I'm going to do this on the next one. So I have the same tangent line drawn, but now I'm going to draw a line between the point 1.51 and 1, 2. And you can kind of tell like this is definitely closer to that blue line than this red one. Like this is much steeper than the blue line, but this one is a little bit closer. And so we're going to find that slope the same way. So we would do y2, which is 1, minus y1, which is 2, and then x2, which is 1.5, minus x1, which is 1. So we get -1 over 0.5. And if you divide that, you get -2. Okay. So it says compare the two lines you draw on, which I did before, which would be a better approximation of the tangent line to the curve at 1, 2. And it would definitely be the second line from 1, 2, and the 1.51. You can tell again, this slope looks much closer to the blue line than this red one. So -2 is a better estimate than -3. But what if we pick a point even closer? So let's draw a secant line between 1, 2, and 1.3 and 1.5 and find that slope. So we'll draw a third line between these 2 points. And we'll find that slope, which is 1.5 minus 2 over 1.3 minus 1. So we get -0.5 over 0.3, which gives us -5/3, or -1.66666. And again, if you look at this, like this purple line looks much closer than even the green line, and especially the red line. So we can see if we keep moving our second point closer and closer to that point that we're interested in the slope, that point of tangency, we get a better estimate. Okay. And then it says, now draw your best guess for the tangent line and measure its slope. Okay, so again, this is a little bit harder because we don't know the exact point, but if I just want to estimate the slope of the tangent line, I'm going to pick where it crosses the x-axis. We're going to say that's like 2.2 maybe, and then comma 0. And then this point again is 1, 2, and we're going to find the slope between those. So y2 is 0 minus y1, which is 2. And then x2 is 2.2 minus 1, and we get -2 over 1.2. Okay, and this time I did get the it's probably because I'm off with my estimation, but I got 1.666. Okay, which was the same thing that I got, and it's probably just because I estimated what this point was. They should be slightly different. So like if I said instead this was like 2.10, or 2.3, like I'm gonna get a different slope. That would hopefully be more accurate. But because I estimated it, it's not 100% accurate. But it is showing us that if we pick points closer and closer, we get a better estimate to the tangent line. So this is the idea behind a limit. We say that as the interval got smaller, the secant slopes approached the tangent slope. This should say that. And the idea of approaches is the idea behind a limit. The limit of a function describes the behavior of the function when the variable is near, but does not equal a specific number. So again, as we moved, like we started here and then we moved it closer and closer. And if I kept moving my point like closer and closer to the point of tangency, and drawing a line, my slope would be even more accurate. And so this idea of moving this point closer and closer is the idea of a limit. And the key thing again is that the limit describes the behavior of a function when the variable is near, but does not equal the specified number. So what does that mean? Like, what is a limit? So a limit is the expected y value a function reaches. The limit only exists when both the left and the right and the limit from the right are equal. The value at the point does not matter. So if you look at this function here, when I trace and come from left to right, my function is approaching this y value of 4. Like we're looking at this point at the x value of being 2. And we see that even though there's a hole here, the y value should be 4 at that point if I'm coming from the left. And if I'm coming from the right, it matches up to the same thing. And so we say that the limit of this function at x equals 2 is 4. And this function g of x is the same thing. Even though the point here is at 2, 6, we don't care what happens at the point. We can see as we trace the curve from the left to the right, the y value is going to be really close to 4, like it's approaching 4. And if we come from the right to the left, we can also see that it's approaching 4. Okay, and so we would say the limit is 4. And how we write that is we write LIM for limit. And then we write x arrow 2. So this is what we're looking at as x approaches 2. And we put f of x here. Remember, f of x is the same thing as y, stands for the function, is going to equal 4. Okay, and this one would be the same thing. The limit as x approaches 2. Now this function they defined as g of x is also equal to 4. Okay, and the key thing is the answer to a limit is always the y value. Okay, so that's just an introduction. We'll get into a lot more examples in the next few videos.